Everything you need to know about organic chemistry, Chapter 1. Now, organic chemistry is a chemistry of compounds containing a carbon element, and that's the common element of all living organisms. This is something everyone taking OChem should know, but let's move on to Chapter 1. Basic concepts in chemical bonding in organic molecules. Now, the important thing about chemical bondings is that valence electrons are the outermost electrons, and those don't want to take part in bonding. So, quick recap. For carbon, right here, it's in the column 4A, so it has 4 valence electrons. And if we look at fluorine right here, it has 7, and it goes down in rows. So chlorine has 7 valence electrons, and bromine also has 7 valence electrons. And these are the ones that take part in bonding, like I was saying. Ionic versus covalent. Ionic bonds are where one atom gives up an electron and another takes it, forming charged ions that attract each other. For example, if we have NaCl, our Na has 1 valence electron, and our chlorine has 7. So it'll be 1, 2, 3, 4, 5, 6, 7. What happens here is that this electron gets transferred over to the chlorine. So our chlorine would have a negative charge because now it has 8 valence electrons, which is 1 over then 7. And our sodium here will have a charge of a positive charge, because it has 0 valence electrons when it has 1 on the periodic table, right? And covalent bonds are where atoms share electrons that fill the outer shell. An example would be hydrogen bonding with hydrogen, and this is a covalent bond because they share electrons that fill the outer shell. And we'll go over more into what outer shell is later down in the chapter. Now, polarity. Polarity depends on electronegativity, and basically electronegativity is how hard atom pulls on its electrons. Where the greater the electronegativity, the greater pull it has on its electrons. Because if you look at this fluorine right here, it's the most electronegative atom, right? It really wants one more electron because it wants to be stable, like this neon. It wants to fill its orbital. So it really wants to hold on to its electrons because it doesn't want to lose any. It wants to gain one, right? But if you look at sodium right here, it wants to lose its electron because it wants to be stable and be like that neon where all its orbitals are full. Because now there's only just 1 in there, so that's not stable. So that's how you conceptualize how much electronegativity each atom has. But you can also look at the periodic trend where it goes to the right and up, or to the right, the electronegativity is increasing. And when you go up, the electronegativity is also increasing. Now, polar bonds is when electronegativity, the difference of an atom, is greater than 0.4. So if you look at a carbon-hydrogen bond, where carbon is 2.5 and hydrogen is 2.1, this equals 0.4, and that is not greater than 0.4. So we know that this is a non-polar bond. But when we look at a fluorine-hydrogen bond, for example, our fluorine has 4, and our hydrogen has 2.1, so it's 1.9. That's the difference. And because it's greater than that 0.4, we know that this is a polar bond. Now, Lewis structures. Lewis structures show atoms share electrons. For example, CO2, I like to count the valence electrons first. So carbon and then 2 oxygens. Our carbon has 4 valence electrons plus the 6 valence electrons from the oxygen. And there's 2 of them, so you times that by 2. And this equals 16. So when we draw CO2, we draw our carbon, and we know it likes 4 bonds. So we draw our oxygens here. And we draw the rest of the lone pairs from the oxygen. And just to make sure, let's count them out. 1, 2, 3, 4, 5, 6, 7, 8. And we would count these again, because I like to think of it as like carbon owning one of these electrons and the oxygen owning the other one. So we will still count those, each side of the bond as 1 electron. So 9, 10, 11, 12, 13, 14, 15, 16, and the same amount of valence electrons showed in our equation, so that's how we know that this is probably right. Resonance structures. Resonance structures happens when multiple Lewis structures are available, and the real molecule is a hybrid, which is a blend of all possibilities. Now, if we were to do the resonance structure of CO3 with a -2 charge, it would look like a carbon in the middle with our with bonds with carbons on each side. And because carbon likes 4, we're going to draw that fourth bond here. And we draw the rest of the electrons. And if we notice that these oxygen has 7 valence electrons, both of these, well, this only has 6. So that means that this is a negative charge oxygen. Whoops. And this is also a negative charge oxygen, right? Because it's the same thing as the oxygen below. And this is the resonance structure of it. But for the hybrid, it's a blend of all of this, right? Or this is just one of the resonance structure, is what I'm trying to say. And that, like, what if this double bond was on, sorry, I could have just drawn an arrow. What if this double bond was on this one? Or what if it was on this one? The molecule would be the same, right? And that's what a hybrid really is. It's a blend of all the possibilities. So drawing it out, we have a carbon and still have the 3 bonds of the oxygen. But instead of a solid line for the double bond, we'll draw a dashed line. And we'll draw on all of them because whether the double bond's on this oxygen, or this oxygen, it doesn't really matter because it's all the same molecule. But we would still draw the partial negative charge on each because each one of these could have a negative charge. Alright, so that's how you do resonance structures. And resonance structures in organic chemistry, and this is basically difference of like how to draw these. The rules are that every resonance must be formed of valence Lewis structure. Atom connectivity never changes. Net total electrons stay the same and net charge stays the same. Only pi bonds move, sigma bonds never move. So we can draw out the sigma bonds because we know that these never move. Wow, that scared me. Not sure if y'all heard that. But we draw out the sigma bonds. And we notice here that there's actually a double bond right here. So we know that in resonance structures, electrons move. So we can say that this double bond is going to move over here and fulfill this carbon so it doesn't have that positive charge anymore. So when we draw it over here, we're going to have the double bond here, but now this carbon shouldn't have a positive charge, right? Because it has its 4 valence electrons, but this one doesn't have all 4 of its valence electrons, so it has that positive charge. Now, valence shell electron pair repulsion theory, or Vespert theory, is when electrons repel each other in a range as far as possible. The groups include sigma bonds, double bonds, triple bonds. These are all counted as the same thing in lone pairs. Now, my most recent video went over and explained all these different shapes and steric numbers and lone pairs and bonds. So I'd recommend watching that or learning through Quizlet or just taking a screenshot and learning all of this. But what you need to know is that you need to know each of these shapes, the amount of steric numbers they have, and this is just electron densities like lone pairs or bonds, and the amount of lone pairs each one has, and the angles for each. Yeah, and that's all you need to know for all of these. I know it sounds like a lot, but it's a lot easier once you get going and start recognizing it. Now, valence bond theory and hybridization. Covalent bonds formed when 2 atoms share electrons, but not just any electrons, unpaired electrons that live in orbitals that can overlap. So if we look at the orbital diagram of the fluorine here, we notice that it has one unpaired orbital. So that's how we know it can form a bond, because it has the unpaired orbital. And because hydrogen also has one unpaired orbital, they can form one bond with each other, and that's how we have that sigma bond right here. And right here, this is just saying that hydrogen can bond with fluorine, even though that this is a p orbital, and while hydrogen has a 1s orbital, they can still bond. Now, this begs the question, what about CH4, right? Because wouldn't this be the orbital diagram? Well, the funny thing about orbital diagrams is that they want all their these boxes full. So this arrow is actually going to come over here and put itself over there. So when we draw it out, let me draw the boxes real fast. This is 2s, 2p, 2p, 2p. And for drawing these, you always want to draw the arrow up first, and up, up. And now we have another electron here, because this one, as we were saying earlier, that this one moves over there. So this is the orbital diagram for CH4. And as you can see, there's 1, 2, 3, 4 valence. And there's 4 bonds that can be made, And just to make it clear, for nitrogen, since it has 5 valence electrons, it would look exactly like this, but with another arrow there. And let's say this is nitrogen, there's 1, 2, 3. There's only 3 unpaired boxes, so it can only form a max of 3 bonds. Okay, I hope that's clear. But what exactly is this 2s and 2p system, right? Well, this is just a periodic table labeling each one. And if you were to find an atom, let's say you wanted to find bromine, which is right here, right? This is for the electronic configuration. There's a 1s squared, because there's 2 of them, and then 2s squared, and 2p to the power 6, because there's 6, and then we go to 3s squared, and then 3p to the power 6, and when we get to 4, it's going to be 4s squared, and because it's connected, it's 3d to the power 10, and then 4p, not 6, but 1, 2, 3, 4, 5, 4p, 5. So basically, this just includes all of them, except, and then you want to include that one. Yeah. So if you wanted to do, let's see, you want to do the chlorine, that's right here. You would do 3p, 5, right? And then this would be gone, but this would be this would be for chlorine, right? Okay. So Vesper hybridization. This is just like the same thing, but whether it's a bond or lone pair, it doesn't matter for the hybridization. And so when the circuit numbers 2, 3, 4, 5, and 6, it's gonna be octahedral, trigonal, bipyramidal, tetrahedral, trigonal planar, or linear. And I like to think of this as like SP 1 plus 1. So it's 2, and SP to the power of 2, it's 1 plus 2 P's. That's 3 circuit numbers. And then 1 plus 3 equals 4. And then 1 plus 3 plus 1 equals 5. 1 plus 3 plus 2 equals 6. That's how I like to figure out how many bonds there are, or lone pairs, on the central atom. And to know a subset 3, I like to think of this, like this just starts at 3. So that's how I like to think of it. But moving on, Vespers are organic molecules. Don't let this trick you. This is pretty simple. sp3 for this carbon, you can see that there's 1, 2, 3, 4. So it's sp3 tetrahedral. And now if we look at this carbon, this one's sp3, but there's only 2 bonds. That's because there's actually 2 lone pairs, So don't forget the lone pairs, because with the 2 lone pairs, that's how we know that it's a sp3. And then sp2, because there's 1, 2, 3 bonds. And sp, because there's 1, 2 bonds. And that's how we know that's linear. And yeah, that's all of chapter 1. I hope this video was helpful, and thank you for watching.